question here for you. Here are my numbers. Yep. There's a sequence of values up there. 3, 6, 12, 24. And then I put behind it dot, dot, dot. Now guys, after the 24, looking at that sequence of numbers, anybody have an idea, and give me a show of hands on this, just don't blurt it out, but anybody have an idea on what the next value in line might be? Isaiah, what do you think?
48.
48. Why are you saying 48?
Because it just doubles at each time.
So you're identifying that stuff is doubling right here. So if stuff is just doubling right here, 3 doubles to 6, 6 doubles to 12, 12 doubles to 24, 24 is going to double to 48. What would be after 48 then? Go ahead, Gavin.
96.
96. Somebody double 96 for me. Go ahead. 192. All right. Guys, we're going to start looking at what we call geometric sequences today. And geometric sequences are nothing more than an exponential growth or decay pattern. Okay? Growth or decay. Guys, look at this common ratio right here. What is 6 divided by 3 right here, guys? 2. What's 12 divided by 6? 2. And so on. 24 divided by 12? 2. Common factor each time is what value? 2. Just like Isaiah said, the pattern is you take the previous value and double it. So a lot of what you're going to look at doing today is say, hey, here's a pattern. We're going to be looking for the next few numbers in the sequence, okay? And this is really a pretty simple section. I think everything that we've done leading up to this section should make this probably the easiest one that we look at throughout chapter 6. So, that idea in the back of your mind right here, thinking about sequences, what type of pattern is occurring to get the next few values in that line, we're going to continue to look at geometric sequences as they would relate to exponential functions. Now guys, how many terms did you give me after the first 4 were listed there? How many terms did you give me after those first 4? You gave me 3 more, didn't you? You gave me 48, you gave me 96, and you gave me 192. Guys, what if I wanted to ask the question, what's the 205th number in line? Would you want to double 205 times, or would you want an easier way to do that? If I would say, what's the 205th number in this pattern going to be? Would you want to double your numbers 205 times, or would you want an easier way to do that? Yeah, I think an easier way to do that, and we'll look at how that happens here today. But guys, let's take a look in the notes right here. Again, don't lose sight of the stuff that we're doing. We are still talking about exponential functions here in this section, even though it's titled differently. We're still looking at exponential functions. So don't lose sight of that. Okay. Guys, 6.5 is titled Geometric Sequences. The question we want to ask is the following. How can you use a geometric sequence to describe a pattern? That's exactly what we're looking at. Find me the next few numbers in that pattern. So in order to answer our question, we need to be able to identify what a geometric sequence is. We need to extend and graph some geometric sequences. And then we're going to turn right around and write some geometric sequences as functions. And for this right here, we have a very nice little formula that we'll discuss. And I think that if you can understand what the notation means on the formula, this will be really easy for you. Okay. All right, so some vocab that's necessary for us today. 2 terms. First one is geometric sequence. I got a volunteer that would read this for me. Thanks, John.
An ordered list of numbers in which the ratio between each pair of consecutive terms is the same.
Okay, this should actually just say the ratio, so get rid of that N. It should say ratio right there. So the ratio between each pair of consecutive terms is the same. So I'm going to go back to that pattern that we had. We had 3, 6. What was after the 6, you guys remember? And after 12 was 48, And I'm just going to put dot, 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 meaning it goes on forever. It says an ordered list in which the ratio between each pair of consecutive terms is the same. In other words, what is 6 divided by 3? What is 6 divided by 3 here? 2. So we're multiplying by 2 each time to go from term to term. All right, so that common ratio would be a 2. And then this talks about what is a common ratio. Well, a common ratio is the ratio between each pair of consecutive terms in a geometric sequence. I'm going to throw up a sequence here. You tell me what the common ratio is. All right. Guys, there's a geometric sequence. What's the common ratio? 4. If I take the 8, I'd have to divide that by the preceding value of 2. 8 divided by 2 would be 4. Guys, is 4 a value bigger than 1 or less than 1? So would this imply exponential growth or exponential decay? Growth. All right. What if I put a sequence up like this? I'm going to write down the common ratio R is 4 for this one. What if I put a ratio up like this? You ready? That second set of numbers, or that second sequence, if you will, 100, 50, 25, 12 and a half, is that modeling growth or decay, first of all? Decay, right? So my question is this: what's the common ratio within that sequence? How would you find that? You just told me it represents decay. So if it represents decay, my ratio better be more than 1 or less than 1? Less than 1. Here I was taking 6 divided by the preceding value. So if I start with 50, what are you going to have to divide by, kids? 100. Let's see, 50 over 100, or 50 divided by 100. Describe to me the pattern right here, guys. What's happening? Yeah, each value gets cut in half, right? So aren't we multiplying both, or the preceding value by 0.5? So what's the common ratio in this, guys? Yep, it would be 50 divided by 100, which is the same as 25 divided by 50. In each case, this is always what ratio? 0.5. Okay, 0.5. Again, common ratio more than 1, are you modeling growth or decay? Common ratio more than 1, are you modeling growth or decay? Okay, and then if you have common ratio less than 1, are you modeling growth or decay? Decay. Like me, I'm decaying. I'm decaying. I'm getting old. And I don't like it.
Not that old.
40.
Oh, big deal, it's 40.
40's the new 20, right?
Yes.
Example 1, guys. Identifying if a sequence is arithmetic, geometric, or neither. Take a look at your patterns right here. 8, 24, 72, 216. First of all, is there even a pattern taking place there? Yeah? What's the pattern? 3? Adding 3 or multiplying by 3? Multiplying by 3. Check it out, guys. If I go 24 divided by 8 right here, what is 24 divided by 8? Okay, we get 3. If I would check 72 divided by 24, what do I get again? 3. If I would do 216 divided by 72, 3 again. I'm going to make a note here on this. When we do division, anytime you do division from one value to the previous value, divide a value by a previous value, we have what's called a common ratio. We have what's called a common ratio. In this case, our common ratio is equal to what value? 3. If you ever have what's called a common ratio right here, if you ever have what's called a common ratio, multiplying by the same value, whether it's more than 1 or less than 1 each time, this will be some type of geometric sequence. Geometric sequences are defined by common ratios. What are you multiplying the previous value by each time to get the next value? So as we classify as a geometric sequence. Okay. Now, in part B, guys, do you identify a pattern in part B? Goes down by 5 each time. So it'd be like adding -5, wouldn't it? Am I multiplying it all this time at all? No. To go from 8 to -3, we are adding a -5. Adding a -5. 3 plus -5 would be -2, wouldn't it? -2 plus -5 would be -7. You are always adding -5. So guys, rather than calling this something that's division of a value by a previous value, if I add a value to a previous value to get the new one, you have what's called a common difference. You have what's called a common difference. And anytime you have a common difference, in this case, what was I adding each time? What were you adding each time? -5. We would say that that's not a common ratio, it's a common difference. How much am I adding to the previous value each time? You have what's called a common difference. In this case, our common difference is -5. You would add -5. If you ever add a value right here, your graph is no longer exponential, but it's considered linear. Now, way back in chapter 4, we looked at stuff that was called this type of a sequence. Anytime you're adding the same amount to previous values, this is called an arithmetic sequence. All right, arithmetic sequence. Anytime you're multiplying or dividing by the same value, it's called a geometric sequence. Now guys, quickly, this pattern up here, letter A, is this an exponential pattern or is this a linear pattern? You're timesing by a common ratio each time of 3, or a common factor, if you will. So is that exponential or linear? How about this? Going up by the same amount each time, adding the same amount each time. Is that linear or is that exponential? It's linear. So what I'm getting at here, guys, is this. If they ask you to determine if something is either geometric or arithmetic, one way of remembering it is, well, if I have an exponential function, what kind of a sequence do you have? Geometric. And if you have a linear function, then you will have an arithmetic sequence. Okay? All right. So there's a ton of stuff going on here. What we're really doing is we're taking all of our terminology right here and we're putting it together. We're trying to decide what groups up with what. So anytime it's exponential, think geometric sequence. If anything's ever linear, then it's what type of a sequence? Arithmetic. All right? Big terms. Big terms. We've done arithmetic sequences this year. It's been a while since we've talked about it, but we've done it. New one that we're going to look at is what's a geometric sequence and how does it work? Okay? All right, do you guys have the stuff down on page 1 right now? Everybody okay there? All right, let's talk about page 2. Extending and graphing geometric sequences. I love this right here because it says write the next 3 terms of each. What kind of a sequence do you have, guys? What's it say? We're going to write the next 3 terms. Now, here's what I want you to start getting used to. In your book, you're going to see stuff written like this. They're going to start using stuff like the following. In a table, you might have something written down like A1. All right, some pretty good steak sauce. Or marinated, right? And I brought the great taste of steak in the mouth today.
Well, it was.
Right? You guys want to share my humor this morning? What is wrong with you?
We're ready for a break.
Tired.
Ready for a break? You get a break soon. Guys, this A1 right here is basically determining which position the term is in. This is like saying the first term in this sequence, or the 1 right here, the subscript 1, really is saying that's the first term in this. So in this sequence right here, what is term 1? You would tell me term 1 is what value? Okay, so 324 has to be term number 2. 108 has to be term number 3. Makes 36 term number 4, right? Okay, these sequences are what types of sequences? They're geometric. So we're looking for a common difference or a common ratio? Ratio. So we're going to take one value and divide it by the previous value. So let's do that. I'm going to find a common ratio R. So in other words, I'm going to go 324 and divide this by what value? 972. Okay, so watch this real quickly, guys. I go 972 divided by, whoops, I've got that incorrect. I would go 324 divided by 972. What do I get there? 0.3 repeating, right? So that means to get my values now, I have to take all these times 0.3 repeating. So I want the next, how many terms here, guys? How many does it say?
3.
So if I've got the first 4 terms listed, then we need to figure out what term 5 is. We would need a term 6 and a term 7. All right? No problem. Guys, again, what was my common ratio? 0.3 repeating. What is 0.3 repeating in fraction form? It's 1/3, isn't it? It's 1/3. Basically, you're taking all these values and dividing by what each time? Dividing by?
So R equals 0.3.
R is 0.3 repeating, yep. Watch what I do here. Grab my calculator. What was term 4 again, guys? What was term 4? 36. So we're going to take 36 times 0.3 repeating. Watch what happens. Ah! What do I get? 12. That's the same as 36 divided by 3, isn't it? Okay, so term 5 has to be what value? 12. Take term 6 and divide it by 3 again. Or I'm sorry, take term 5 and divide it by 3 again. What's 12 divided by 3? 4. Now we're going to turn around and take 4 and divide it by what? Divide it by 3. All right? You're going to get an ugly decimal. I'm just going to leave it as a fraction now because I can't simplify it. Next term is going to be 4 divided by 3. I'm just going to leave it as an improper fraction, about 4/3. So if I say, hey, here's the start of a geometric sequence. Here are the first few terms. Can you list the next 3 for me? Identify the pattern and then figure out the next 3 terms. Can you handle that? Can you handle that?
Yeah.
All right. Let's look at this next one. How about a pattern from 7 to -14, -14 to 28, 28 to -56? Anybody see a pattern? What's going on here to go from one value to the next? Jacob, you see it? You times by -2 because, guys, if I work backwards, what's -14 divided by 7? It is -2. 28 divided by -14 is -2. -56 divided by 28 is -2. So in this example, to find terms 5, 6, and 7, or your next 3 terms, you're going to take the previous value times what? Common ratio again. What do we say the common ratio was here, guys? -2. So to get term 5, describe to me how to get term 5. If this is my fourth term, describe to me how to get term 5. So you're going to go -56, right, McKenna? -56 times -2. I end up with 112. Now we're going to use that 112 to figure out term 6. Take 112 times what value? -2 again. All right, so take this times -2 again. What do I get? -224. Finally, A7, seventh term in this sequence. Take -224 times -2. You end up with 448. Find your next three terms. Simply identify your pattern. Once you've identified your pattern, you're going to take the previous value times your common ratio to get your next value. Okay? Yep. It's times. It was times 0.3 repeating here too. Timesing by 1/3 is the same as dividing by 3. Okay?
So divide by your times.
Yep, we were timesing by 0.3 repeating there.
So if I take -56 times
Mm-hmm. Got it? And then you're going to go 112 times -2 again to get your next term, okay? All right. So guys, what's this look like in terms of geometric sequences? We kind of talked about this already. Guys, it says graph the geometric sequence. 1, 2, 4, 8, 16. Okay, yeah?
I got a joke for you.
In a second. All right. Guys, what's term 1 equal here? What's term 1 equal? 1. Okay? To graph a geometric sequence, this is how stuff looks. Basically, term 1 is 1, so you're applying a point really 1, 1. All right, term 1 is 1. So I'm going to go down here, and what you end up really plotting is the point 1, 1. All right? What's the next value? What's the second term equal, guys? Isn't it 2? So what you're really doing is graphing 2, 2 now, aren't you? So I'm going to do that. Go right 2, up 2. How about your third term? What's the third term? What's the third term? 4. So you're really graphing the point third term, 3. That third term is 4. So 3, 4 is what you're really graphing. So right 3 and up 4. There's that point. What's the fourth term? Fourth term in here is 8. So let's see. That's like plotting the point. Term 4 is 8. That's like plotting the point 4, 8. What's my last point, guys? What's the fifth term? 16. So that would be like plotting the point 5, 16. So I go right 5 and up 2. 16. I think I've got this 1, 2, 3, 4, 5. Tell me if I've got that plotted correctly. Does that look right to you guys? Hey, quick question then about that graph. 5, 16, 4, 8, 3, 4, 2, 2, 1, 1. Does that look linear or does that look exponential to you? Yep, it looks like it's going to curve in and start shooting straight up, right? Boom, like this. So when it says, what do you notice about geometric sequences plotted like that? What do you notice? It appears to be what type of a graph? It appears to be exponential. It appears to show exponential growth. So I'm going to write this down here. Appears to be exponential. It appears to be exponential. So geometric sequences appear to be what type of function? Exponential. All right. Now again, keep in mind we have to have b greater than 0 in order for that to happen. The negatives kind of throw stuff off. We won't talk about that too much. All right. Identifying the next three terms. Can you handle it? By the way, what would be the next number in this sequence? What would be the sixth term in this sequence? 32 would. You're just doubling, right? Okay, very good, Jacob. Okay, anybody need more time with page 2? Are we good? Well, I know the answer to that. You guys are great. All right. You know why I know that? Tony the Tiger told me that.
Who?
Tony the Tiger told me you guys are great.
Oh.
Get it? Get it? Oh, okay.
That was
I
terrible.
get it. I get it.
All right. Hey, example 4. If there's anything that's question or stretching.
I was actually stretching.
Okay. Example 4. This is probably the most important thing that we're going to take out of today. All right. This is going to be your most important piece to take out of today. Guys, there's a nice formula out there that's called a geometric sequence formula right here. And we use these formulas right here to figure out what maybe a 10th value would be in a sequence, or maybe the 100th value, or maybe the 500th value. Okay? And it says write an equation for the nth term of the geometric sequence. And I'm going to just make up a sequence here that's geometric for us. All right? And here's your sequence. I'm going to write it out like this. Write this table down right here real quickly, okay? Write that table down real quickly. So guys, the way I've set that table up for you guys to visualize this is the following. It says that in this sequence, term 1 is what value? Term 2 is term 3, 9, term 4, 13.5. First thing it says to do is write an equation for the nth term of the geometric sequence. And we're going to use that formula up there that states the nth term on the left, this nth term on the left right here, is equal to your first term, which is a1 times r to the n minus 1. Let's establish some parameters here real quickly. Okay? Anytime you are writing a function for the nth term of a geometric sequence, you have two jobs. Job number 1 is this. Find your starting value or your first term. Find your starting value or your first term and plug it in. Second then is this. Find your common ratio. Common ratio R. So what this essentially comes down to is the following. You need to find something to plug in for A1, and you need to find something to plug in for R in order to write a function. You need to find something to plug in for A1, and you need to find something to plug in for R for this. And I'll show you how this works.
That's only 2 steps.
It's only 2 steps, but then we're going to take it a step further. Okay, to write an equation for the nth term of the geometric sequence, here's what I want you to understand. this n value that they talk about sometimes is like your term number. So like right here, what's the n value here that I'm pointing at? What's the n value here that I'm pointing at? 3. So when we have to go ahead and figure out what a of 10 is, what are you going to throw 10 in for? N at some point. We have to be able to write the equation first before we can figure out what the 10th value in that sequence is going to be. So here we go. I like to go ahead and write the formula every time for a geometric sequence. So the formula that I'm going to choose to use here is the following. We're going to say a of n. That's going to equal my first term, a1 times r to the n minus 1 power. All right, step 1, first term. Do you know the value of the first term in this table? It's 4, isn't it? Okay, so here's what this is going to look like. We're going to say the nth term of this sequence is going to be my first term, which is 4. We're going to plug 4 in for the first term. Now, this is like a starting point in an exponential function. This is like my a value. Then, we need to find that common ratio. Now, what common factor is stuff growing? Well, I've already told you this sequence is geometric, haven't I? So couldn't I find a common ratio by simply taking 6 and dividing by what, guys? 4. 6 divided by 4. Somebody punch that up. 1.5. To make sure that this table isn't goofy, somebody do this for me and go 9 divided by 6 and tell me what you've got. All right, one last crazy question. What do you think I want you to check finally again? 13.5, divide that by 9. See where you're at. 1.5. So what's your common ratio in this? 1.5. Okay, now, how do I want to do this? Let me think a second. I'm going to leave it as that. Okay, I'm going to leave it like that. Because there are some manipulations we can do with this, I'm going to leave it just like that and call it good. All right? This here is your equation that you need to model that geometric sequence. Now, the next thing that they go on to say then is find what? Find the 10th term. Okay? So what we're really going to do is we're going to replace this a of n right here to 10. We want to say, hey, the 10th term then.
So
My 10th, yep. My 10th term in this sequence would be the following. It would equal that a1 value of 4 times my common ratio of 1.5. Now right here, kids, this n minus 1 right here, n minus 1 is the power they're using. What am I plugging in for n if I want the 10th term? 10. So this becomes to the 10 minus 1 power. What is 10 minus 1? 9. All right? 9. So if I wanted to go ahead and extend this table all the way out here to A10, what's the 10th term in this sequence? Here's what you're going to do. You're going to take 1.5 to what power first, kids? 1.5, raise it to the 9th power. So let me do that. And then what do I want to multiply that by? Times that by 4 in the end. And man, we get a really ugly number, but do we know what the 10th term is now? Yeah. Because this here says n minus 1 is my exponent. I plugged in 10 right here, and that 10 minus 1 gets you an exponent of, okay with that? All right. So when I evaluate this, remember this phone number for me. Area code 153-773-4375. Having your numbers up here. Digits are up here, buddy. All right. Can you guys remember that? You think I can remember that? No, I'm going to try and remember. Was it 153.7734375? I don't remember. 7734375? Now guys, you're going to start being asked to find the 50th term, the 120th term, Is that formula easier to define terms down the road, or do you want to multiply stuff out 120 times? Which way is easier, formula or multiplying 120 times? Formula, you bet. Okay. This, mucho importante. Did I say that correctly? Where are my Spanish people at? Where are my Spanish speaking people at? Mucho importante. Is that right? Pretty sure. All right. I was expecting no. All right. I was expecting no. All right. So formula for geometric sequences right here. What's A of n represent? Well, it represents the nth term. How about A1? Not a steak sauce. What's that represent? First term. Very good, Mary. And then this R is your common ratio. Excellent. Excellent. Okay. Well, let's look at this last example here quickly. Do you guys have down what you need right there? Give me some sort of sign you're alive right now. Everybody have that?
Yeah.
All right. Okay. Volunteer to run through 5 for me as this relates to geometric sequences. Who would like to read that, please? Volunteer to read that for me. Oh, come on, you guys.
Clicking the zoom out button on mapping
Thank you.
website doubles the side length of the clear map. After how many clicks on the zoom out button is the side length of a map? 5,120.
Very good. So you guys have all done this before. We do this in decimals all the time. We keep zooming out, right? And things get bigger and bigger for us. So here's the situation in this, guys. It says by clicking that zoom out button on a map, we got to find a number of clicks it's going to take to get us down to 5,120 miles. So guys, on a map, if I click one time, what's the length of the map that we see? How many miles of the map do we see? 5. Now on this map right here, if I click a second time and zoom out, if I zoom out, we see more of the window. Okay? So the values are getting bigger and bigger and bigger. And each time I zoom out here, guys, this is how many miles you see on the side. Now, they want us to figure out how many clicks it's going to take to get to, eventually, 5,120 clicks. All right, 5,120 clicks. So here's how we're going to handle this. Guys, this is going to be a table just like the following up here. It's going to say, well, you got term 1, term 2, term 3, term 4. Really, guys, term 1 is what value? 5. When I say when my zoom out click is 1, it's like my first click. This is like your A1 value of 5. Term 1 is 5. Term 2 is, I don't know. Term 2 is 10. Term 3 is, okay, and so on. We keep on going. This is term 4. Well, let's use that formula right there. Let's plug in A1 and maybe R and see if we can't first of all write a formula for this table. Okay? Because out here they want to know what click, we're trying to find the end value that would get you a side of how many miles. How many miles do they want that side to be, guys?
5,000.
Okay, let's type in that formula. I'm going to write the formula again. States the following. It states my nth term, A of n, is going to equal A of 1 times your common ratio to the n minus 1 power. Okay, what is the first term, kids? What is the first term? Okay, do you know the common ratio? What's your common ratio with the arrows I've drawn? 2. All right? Guys, what do I want a sub n to equal right here? 5,120. We have to figure out an n value to put in here such that 5 times 2 to the n minus 1 power is what value? 5,120. Okay? Now, this is very difficult to solve algebraically. This is very difficult to solve algebraically. So if something is difficult to solve algebraically, where do I tell you to go? Decimals. Decimals. So let's check this out. I'm going to jump into decimals quickly. And guys, what we're going to end up doing is we're going to find a point of intersection. We're going to put this in the field to the left and this into the field to the right. Now again, pay attention to what I do here because things are foreign, they're different. I'm going to jump in here. Come on. We have a left side and a right side of the equation. Is that correct, gang? Okay, here we go. What do we have on the left side, kids? 5,120. So I'm going to go in here and simply type y equals 5,120. Are we okay with that? Then I'll change the window here in a second. What's the right side of the equation? Y equals 5 times, was it 2?
Yeah.
And then it was to the n minus 1 power? Alright, so I need to raise a power. Since I have an n minus 1, put parentheses up here. I'm going to call it x minus 1. And we're basically looking for the point where these two lines cross. Now guys, see your y value up here? I need to change my window, so I'm going to go into settings. I like the x-axis as is, but the y-axis, pick some values around 5,120. How about 5,000 and 6,000? Is that okay? So I'm going to pick a value of 5,000 here, and maybe a value of 6,000 right here. And let's just see. Does that show up anywhere? Does my graph cross anywhere? I don't see it. I don't see it. Oh! Drag around a little bit. Do you see where my lines are meeting? Okay, so I'm going to click right here. And it appears to me, guys, n is what value? Or the x value, if you will. What is it? 11 right here. So guys, when you get your equation written for something like this right here, put the left-hand side of the field in as y equals, put the right-hand field in as the side y equals. Figure out where they cross. So what do I want to say right here, kids?
5,120 equals.
Okay, so we got an n value of 11.
Yeah.
So it takes 11 clicks to view the map with the distance 5,120 miles per side. Okay. Guys, have a great day.